Okay, so in this video, we're going to look at inverting inputs and outputs to the basic logic gates. So we're going to look at the effects that adding inverters to our basic logic functions has, and how we can create other logic functions or operations by adding inverters to either the output or the inputs or both. And see how we can create that and look at why that is useful and can be beneficial in certain applications. Okay, inverters can be added to the basic gate to change its logical operation. So by either doing inverters on the output or inputs or both, we can change how the final output behaves. So this can be beneficial because we can reduce the number of chips that we have to keep on hand. If we can use one or two chips and then use inverters with that, we can reduce the number that we have. Or if we don't have a certain type of IC chip available, we can substitute by inverting inputs or outputs to one of our other gate functions that we do have. Another benefit of this is to reduce the number of chips on a circuit board. So if we can utilize all the gates on one IC chip by adding an inverter to the inputs or outputs, rather than having to grab another chip for just a single AND function, let's say, then that can reduce costs and save space as well. Alright, so to understand this, I made this chart to show you the effects of inverting the inputs and outputs. Okay, so for this, we're just looking at the AND and NAND and OR and NOR and the effects of inverting the inputs and outputs to those gates. Alright, so we will talk about the exclusive OR and exclusive NOR. But that behaves a little bit differently, so we'll get to that later. But first I want to go through this. Alright, so I've colored these to let you know what is what. So the green arrows here indicate the effects of inverting the inputs to a logic gate, and the orange arrows indicate the effects of inverting the outputs. Alright, so let's start with our AND. So if we invert the output to the AND, that's going to make it a NAND, which is basically what a NAND gate is, which we've already talked about. It's just an AND with an inverted output. So if we actually take an IC chip that is an AND function, invert the output, that makes it a NAND. If I take a NAND gate and invert its output, it's going to take it back to just a basic AND function. So if I have a NAND and add an inverter to its output, it's basically an AND with two inverters on its output, and the two inverters essentially cancel each other out, and that leaves us with just a basic AND function. Alright, so the same goes for the OR. If I invert its output, it becomes a NOR. If I take a NOR gate and invert its outputs, again, two inverters cancel out, but makes it an OR function. Okay, so that's pretty straightforward. Alright, so for inverting the inputs, however, we get the opposite type of logic and the inverted form of that, essentially. So that's why the arrows cross in this diagram. So, for example, if I have an AND and I invert its inputs, I'm going to get a NOR function. So that's why I said you get the inverted opposite operation. So it's going from an AND to an OR function, and it's the inverted form of it, which is NOR. Okay, so that's what I mean by that. So if I have a NOR and invert its inputs, it's going to go to an AND function. So if I have an OR, invert its inputs, again, it's going to go to the opposite inverted logic, which would be a NAND. If I have a NAND, invert the inputs to it, makes it an OR function. Okay, so that's the operation of inverting the inputs to those four logic functions. All right, and then you can also invert the inputs and the outputs to a gate. All right, so if I have an OR gate and I invert the inputs and the output, I just have to follow two arrows. So if I invert the inputs, makes it an and then inverting the output makes it an AND. So if I have an OR with the inverted inputs and outputs, I get an AND function. Same goes if I had an AND with an inverted input and output, goes to an OR function. So you just have to follow two lines when you do both. If I have a NAND with an inverted input and output, input takes it to an OR, output takes it to a NOR. So a NAND with the inverted inputs and outputs gives me a NOR function. Okay, so this chart will help you determine what the output equivalent operation will be for those four logic functions. All right, so next let's just talk about the exclusive gates. Okay, so they're a little bit different in the way they behave just because of the nature of how the exclusive gates operate. All right, so if we look at inverting the output of the exclusive gate, it's just going to change it to the opposite exclusive operation. So for example, if I have the exclusive OR gate and I invert the output, that's going to make it an exclusive NOR. If I have an exclusive NOR, invert the output, it goes back to just a basic exclusive OR function. Okay, so just really the same way inverting the outputs affects the AND and OR gates. All right, so that's pretty much the same. The inputs, however, are a different situation. Okay, so remember the exclusive gates are comparison gates. So they're looking for likes and unlikes on the inputs. So if we invert the inputs to the exclusive gates, it actually doesn't change anything in the exclusive gate operation because the likes and the unlikes are still going to be in the same place if we write out the truth table. So if I put in two zeros, those two get inverted so they become two highs. So the output's still going to be low for an exclusive OR. If I have two highs, they get inverted to two lows, it's still going to be a low output on the exclusive OR. If I have a high and a low, that's going to get inverted to a low and a high, which is unlikes. I'm still going to get a high. So the likes and the unlikes are still going to be in the same place. So therefore, inverting the inputs to the exclusive gates changes nothing with its operation. Okay? So that's why it's a little bit different. So for the AND, NAND, OR, NOR, use this chart. For the exclusives, the output changes it to the opposite. Inverting the inputs changes it to nothing. All right, so we're going to look at a few examples here of doing that, either inverting the output or the inputs or both. So this is not all the possibilities, obviously, but this is just a few to give you some idea of how this works. All right, so the first one I have an AND gate with an inverted output. So I have an AND, invert the output, makes it a NAND function. All right, so that's pretty straightforward. All right, so the next one I have a NOR gate, and I'm inverting the inputs to that. So if I have a NOR and invert the inputs, that's going to give me the equivalent of an AND logic. So if I look at my actual final output here on Y, it's going to behave like an AND gate. All right. So the next one I have a NAND, and I'm inverting the inputs and the output. So here on my chart, I just have to follow two lines. So the NAND, I invert the input, makes it an OR, but I'm also inverting the output, so I get a NOR function. Okay? So just follow two of those lines to get where you need to go. And then the next one here, I've got an exclusive OR with an inverted output. So remember we said with that, it just changes it to the opposite. So that's just going to be an exclusive NOR function. And then this last one, I have an exclusive NOR with inverted inputs. And remember we said here that the likes and the unlikes will still be in the same place, so it doesn't affect anything. So this exclusive NOR will still work like an exclusive NOR function, okay, because it doesn't change anything. All right, so again, this is not all the different combinations, just a few to show you how that works and how we can use the inverters with the logic functions to get other types of logical operations. Again, to cut down on the number of chips, or if we don't have a certain type of IC chip available, we can make it work with using inverters. Okay, so you could go through and make out truth tables for these and actually compare the signals and look at the final output, and you would see that for each of these, this would be the result you get. Okay, but by using this chart, we're cutting out all that, saving us time, and that will show us what the equivalents will be for each of these. All right, so that's the effects of inverting the inputs and outputs to the logic gates. If you have any additional questions, let me know. Thank you.